Okay. Hear me? Let's start. Okay, so we got towards the last parts of the course. Any questions until now about the course? I'm not here every week, but someone asked me about the test. Are the papers for the test? The papers you're presenting, the answer is no. But still, continue to come to the classes. It's important. Maybe not for you to see a paper, and also for to be we choose these papers because they're important, but also for you to support your friends. So, although it's not in the test, I encourage you to continue and come, or want you to continue. Okay, so we got to the last part of the course, and we'll talk about the motor system, and this will be divided to 4 parts. Today I'll talk a very general introduction about motor system. It will be a more fun class. I'll show some movies, and it will be more easy, not a lot of details, and towards the end there'll be some more details. From Thursday, I'll talk about motor cortex for 4 hours, and then there'll be papers. After that, we'll have 4 hours of cerebellum, of Yossi Yarom. And then last but not least, Chagai will talk about the basal ganglia for 6 hours. So that's what we have until the end of the semester. Also in the cerebellum, there'll be papers, of course. In the basal ganglia, we don't have papers because we didn't have time or students for it. Okay. So again, questions? Anything you want to tell me about the course? It's opportunity? Nothing? Everybody's happy? Good. As I said, I'm not here, but I do talk with the teachers, and I know more or less what's going on. Okay. So we'll talk about an introduction to the motor system. The talk will be divided to 3. We'll talk about general concepts about the organization and planning of movements, what are the challenges of movements, what kind of movements we do. That will be very more, I would say, general part. I'm not trying to be comprehensive. We have 2 hours. These I'm talking about concepts that it's important for you to know. I'm not trying to fully explain each concept, what I'm trying to what it means and all the depths of it, but just for you to be at least recognize what are the problems. I'll talk a little bit about muscles. I don't think you were taught in the basic course about muscles, right? So I won't talk about the contracting mechanism of muscles, but how the brain controls them, how action potentials control muscles. And I strongly, highly encourage you to go to some textbook. I have here Condell Schwartz. Has a chapter about muscles, about really the mechanism of muscle, how muscle actually, how does the action potential lead to a contraction of muscle. Really interesting. Not very complicated. Just read it. I think it's important. And then I'll talk maybe about the basic 2 examples for the most basic behavioral reflexes. I'll give 2 examples and show what are the neural mechanisms that lead to these reflexes. Okay. So why do we have brains? Any ideas? So you can learn this class. That's important reason. Something like egocentric. Survival in what sense?
Pretty much everything. I mean, so we can get the things that we need, shelter,
Good.
water,
Okay.
reproduction.
Production, that's important.
You predict what's going to be.
But why do you predict? What do you care? You need to? To integrate, but why? What do I care? I can integrate, learn math. I don't think. Exactly. We want to act in the world, right? Basically, if you can't do anything about it, there's not much reason to know it. An example for that comes from this creature, which you might hear again and again. Did anybody hear about the sea squirt? Nobody. Okay, good. So I'm the first. It's exciting. So this is lives in the ocean, and here you can see a picture of this creature when it's an adult. It just sticks to the rock in the ocean and just sucks water and filters food from it. That's all it does as an adult. But as a larva, when it's a young creature, it looks like this. It swims around, and it has even something that looks like an eye, and it has controls the world, and it swims until it finds its rock. So it swims until one point it finds the rock that it wants to sits on this rock, and then it has this metamorphosis. It changes a shape, and the first thing, or one of the first things that it does when it changes shape, is to digest its own brain. Okay. And so this is a well-known story in neuroscience. And the idea is that if you don't need to move, then there's no reason to have a brain. So this is the motor part. So this is my way to motivate you to understand that motor is important. So all what we're doing is related. The way we think is for motor behavior. And this is just a maybe extreme example. Of course, I'm exaggerating, and I understand there are other. We can think without moving, but generally the basic reason for thinking is to control the world. And Charles Sherrington, did you hear about him? Here's the name. So one of the pioneers of neuroscience, electrophysiology. I will have some example of his work later, not today, but on Thursday. And he said, I took this out of context, but I encourage you to go and look for the context. But the point was that he said that life's aim is an act, not a thought. Okay, so the reason we move is our goal is to act on the world and control it for all the reasons that you said, reproduction, for getting water, for anything, but it's not thought. Okay, so that's my motivation, and now you all understand that motor is really, really important because that's why we have brains. And I want to show you how good we are and how well our brain evolved for controlling the world by comparing humans to computers. What are we good and what are computers good? So here is the example comes from chess. And the part of these talks, I didn't say it, just to disclose, part of these talks, I took part of the slides or the ideas I took from a talk of Daniel Wolpert. Did you hear about him? He has a TED talk. You can go and look at it. He speaks very nicely. So part of the slides here come from his ideas, or his talk. It's not his originally. So we can think about comparing computers to humans in chess. So we know now that here you can see Kasparov playing chess against Deep Blue. All know the story. So this is a match that went, and sometimes in the 1990s, the first time a computer won the world champion in chess. There was a whole debate about, Kasparov became paranoid afterwards. He thought that somebody controlled the computer. Never mind. Anyway, today we know computers will be eventually, or are eventually, much better than the best chess player. For sure, average computers, better than an average human in chess. Well, so computers are already, so if we think about reasoning, just abstract reasoning of rules, we know now that computers are already better than humans. So that's in terms of reasoning. But when we think about actions, again, we can think about it as chess. Even a 5-year-old kid could beat the best machine in just moving things on a board. So we do this effortlessly from when really, really young. We're really, really good in this. All our system is tuned for moving. So in terms of reasoning, computers probably better. Or at least in some of the tasks, and in terms of moving, we're still much better than computers. And here are two movies. So this is it's a little bit old. So this is from I think 2010, where we looked at the state of the art of computers, and this is an example for a not trivial task of pouring. Okay. So what the goal here is to pour the water in the bottle into the cup. And you can see something that you do on a daily basis quite easily. You can see that a computer, you can do it okay, but still it's not smooth and nice as you can do it effortlessly. Seems you're having a hard time with a computer. But still they can do it. Today, you go to the internet, you see like there's robots today that are much better in walking. A company called Boston Dynamics. Go search it in the internet, really nice. But still, they're good, they're getting better, but they're still not where we are. And here's another example from for the
Super Hands presents Emily Fox.
That didn't work. But we will make it work. Sorry for the noise. Let's do this. Let's try fixing this. So, my computer doesn't like this. Yeah. Let's see this. Let's see if it works again. So, you are the girl that did that? You know the movie? This is really annoying. How will I do it without? Okay, we'll do it without voice. That was that. One second. Okay, so who said you played it? You know the game, so you want to explain what we do, what's the goal?
You just have to take a stack of cups and build like a pyramid out of it, and then collapse it. That's what you get.
Let's. Okay, so this is the here's a picture that was started from here. Okay. So you see this girl, she has to move the cups in some kind of a very accurate and a specific way. So here's the movie. Here, this is how good humans are. Sorry for okay. Yeah. So after that she became the world champion in cup stacking, I think. So, so we're still better than machines in moving in these kind of movements. But why is everything stuck? This is not good.
Is there an example of a computer trying to do that?
No, I'm not aware of it. It might be very good, right? Because it's a very organized way to do it. But yeah, generally, but the idea is that we still are better. Yeah. Let's try last time. I hope this works now. Okay. Good. So we saw that we do all these things very effortlessly. We saw it's a bit hard for computers. Maybe some think they're better, others they're worse. But why is it hard? What are the challenges in studying in controlling movements? Any ideas? Error correction? What do you mean? Why do we have errors? What?
If it touches something and it can't take into account everything that moves. If you only isolate the system enough that moves only because the machine moves it, then it's okay. If you have other things affecting it.
So you're saying the context is important, right? It's not that you do everything in a very controlled environment. There are all kinds of factors that depend, but the behavior needs to take them in account, okay? And you said also error correction, which is related. But generally, yeah, what happens when something is not predicted? How do we deal with that? So that's another challenge. Are there any other ideas? Anything we think about?
Fine-tuning, like, to be really precise.
To be very precise? Okay, so you're saying we need to be, so what's the problem in being precise? Why can't you be precise as much as you want?
So you don't talk about the comparison with computers anymore?
No, generally, yeah. Also, you can take ideas from computers.
Because you have to, like, when you hold the water, you need every time to move slowly the bottle according to the weight of the water.
Okay.
How to, at the beginning, do it slowly and then faster.
So you're saying now, you said two things, I think. You said one thing. You said you need to be very precise. So I think you're hinting for the idea there could be imprecision, so it could be noise, right? Noise and all kind of stuff could be a problem, right? And you need to compensate for that. And the second thing you said that the task could be very complicated. Understanding the world could be complicated, right? Just understanding what is the problem, the liquid, the dynamics of the liquid. That's something that our brain solves somehow, but clearly we don't all have all the equations for that, at least not implicitly in the brain, explicitly, yeah.
You also have to see wells. You want to be able to thread a needle, let's say, or...
So, good.
I don't know if that's...
Yeah, that's good. That's good. So you're saying just gathering the information for what we need is hard, and we need to be very, very precise. That's what I think Matan said. And there could be, again, the noise, right? That's basically the problem. Noise either in how good we are in identifying small things, or you said there could be small movements of our hand that are not really controlled, or small things that can be a problem, right? Yes?
I don't know if the name mechanism is correct, but kind of different mechanisms. We have like reflex and we have movements that we were planning on doing. So it's different mechanisms again.
Okay. I'm trying to. So you're calling it different mechanism.
But I might be not.
No, that's fine. My ideas are good as yours, or maybe yours are even better. So I'm trying to. So you're saying there's some kind of. So we have, I would say, hierarchical system, right? We have some reflexes, some very simple motor actions, but at the same time, we also need to use the same system to do very complicated things. We take them into account, right? So the brain is not just sending a feed-forward signal, do this, but needs to take into account how actually the things are done at the level of reflexes. And there's also another level, the muscles themselves, right? So the muscles themselves are not simple things. You need to take into account all the properties of the muscle to actually act on them in the right way. Yes?
We usually do a number of movements together, like walking and,
Some can do. I can't. Yeah, but that's true, right? So you're saying, I think, yeah, there's complexity of the movement because you need to do many things at the same time. Okay, so all these are great ideas. I'll tell you about some mine or some that I have here. Again, yours are as good as mine. So here, these are examples. It's not comprehensive, but just some kind of example of what are the challenges that we have. So we think about objects, simple objects, as having, something moving very linearly, has 1 degree of freedom, or something can move on a single line and goes forward and backwards. But actually, we can do the same thing, the same goal accomplished in many, many ways. So I want to catch this cup. I can go like this and catch it, take it, right? My goal was to hold the cup, but I can also do it like this, right? It doesn't seem they're a very efficient way, but it could be done. So we have a lot of degrees of freedom in actually acting on the world, and the brain needs to choose one of them, right? So in a sense, it's a problem with many, many, many dimensions of what we can do, and we need to choose one way. And one question that arises from it, what is best in the way that we choose? Is it good? Maybe there are better ways to do it. And what are the constraints that lead us to do that? So that means that, so if we have an endpoint for getting to an endpoint or goal, we have many, many ways to get the goal. And this is true in many levels, in the level of just picking up cup, but generally in life we have goals that we can get different. We want to finish our PhD, you can go to different labs, you can do many different things. You go to LSEC, you can go to a different program. But also in very simple sense, in very simple motor sense, we need to have many different ways to do our goals. Okay, so that's one thing. Another thing that you mentioned, I think you talked a little bit. I think it was in the background of many of your ideas, was that there's noise, or there's some precision that we want to do the behavior, and then there's noise in the system that bothers us. So noise could come from many sources, as you mentioned. Could come from the sensors. We can think of that as sensory noise. Could come from the motor, from actually the muscles. But it also can come, and that's probably the main source for the noise. And there's many works that show that the noise can come from the brain itself. Okay. So you want to do something very, very precisely, but then suddenly you think about something else. In a sense, it's a noise for you in the task that you're doing, and that will bother you. So I think whoever mentioned the two tasks, you can think of doing two tasks as noise for each task is a noise for the other task in some sense. So there are all kinds of sources of noise. We can think about what are the properties of the noise, and here is the example. It turns out that in many, many cases, the noise is signal dependent. So that means that the stronger we try to do something, we want to lift the weight. The larger the weight, the more noise we'll have in our action. And this is just showing that it's not, the details here are not very important, just illustration. So we have your time, and then at one point you need to do some kind of motor command. Let's say this is some kind of power you need to in this task to power of the hand, let's say. And then you see that the red line is the target power, and the black line is like the fluctuation, the actual power that was measured. And you see that in low, when the size of the power is 1, you see that there's small fluctuations. And then when you go to higher powers, you see larger fluctuation, and the size of these fluctuations is dependent on the size of the signal. So it's signal-dependent noise, and this is the type of signal this is practically the type of noise that we have in our movements. Was shown in eye movements, was shown in our movements. And I'm showing this is just an example to show how people went to this question of why we choose the kind of behavior that we choose. And this is the work of Daniel Wolpert that I talked before. And his claim is that the behavior that we choose, the pattern of the behavior that we choose, is selected in order to minimize the noise. Okay, so he's saying, and this is it from his example, let's say you want to move your hand from here to here. Okay, so this is the hand, and here you can see this football is not a football. It's a distribution of the endpoint position given the noise that the brain has. Okay, so if you do this kind of movement, you get this distribution of noise. But now if you decide to do the different kind of movement, this curvature to this kind of curvature, you get a bigger football, which means a larger endpoint variability.
You're talking about this kind of noise, like tremoring, or?
General noise. No, it's not just tremor. It's overall, even if without tremor, if you have this kind of behavior, the noise will be larger if you choose this kind of a pattern than this kind of pattern. Okay.
It's not clear why larger movements produce more noise.
That's an excellent question, and Daniel Wolpert's idea, and was that this is noise that you can think of as noise in the muscle, that the muscle is like that. But that was in the 1998, I think his paper came out. But then when people actually looked afterwards, and they looked in the brain, they already saw signatures for this noise. So the idea is now, and I did this in eye movements, let's look at now in an eye movement, and we can look at the variability in the eye movement. If it's all in the muscle, we wouldn't expect to see the signal related to that noise. But then when you go and actually record neurons in the brain, you see that the noise in the behavior is correlated with the noise in the neural activity, which means that it can't come just from the muscle, but it's actually a central thing. So we know it is central, and there are all kinds of sources for this. There are sensory sources. In the sensory system, there is noise. There's noise in the motor. There's noise in the motor system. Generally, the brain is a very noisy environment, and it's an active area of research. Where is it coming from? The bottom line is that the pattern of noise will be signal dependent. The larger you do something, the larger in some sense something is, the more noise you have. Yes?
What was measured in the previous slide?
What was measured? So this could be like the force. If you hold something and you need to put some kind of amount of force, then the amount of the noise in the noise in the force that you produce will be proportional to the amount of power you need to extract. But it's generally the same thing was shown, as I said, in eye movements, which you don't have loads and you don't have to, it's just when you do faster movement, you have more noise. It's just a general principle, something that we know, and the question is, this is what the system needs to, these are the challenges that the system stands before. And the idea, Daniel Wolpert's idea is that, okay, we have this, and the trajectory that we choose is actually such that it will minimize the amount of noise. This is an example for optimal control where we have a problem. We have some kind of problem to do something, and there are some kind of constraints, and we have some goal. a cost function, you can think of this, which we try to minimize, and we have the trajectory emerges from this cost function. We can think about other cost functions. We can think about the cost function of being more smooth. The two things are not mutually exclusive. Being less noisy and being more smooth is related. You can think about different kind of costs. Maybe your goal is different. Maybe the amount of noise in the behavior depends on what your goal is, right? You can think of this in a very large scheme of, again, let's say, doing a PhD. Maybe you have more noise. Maybe you'll go less to Facebook if you're doing a PhD than you're doing something else. I don't know. That's a really high cognitive idea. But also in our behavior, when we do some very specific task, so my goal is to catch this cup, maybe there'll be a different pattern of noise than if my goal is to catch something else, which is more heavy. So there can be different. The goal itself of the behavior could affect the pattern of the noise. It could be a different cost function, or could determine how we do our movements. Okay. So another challenge comes from something that you mentioned, the context. I want this movie to work. Let's make it work. So as I said, we do our behavior in many different, right? We do, maybe I'll turn it off, set it here. So we don't work in void, right? There's a context, and could be very complicated, could depend on many, many things. And I want to show this movie to explain what do I mean by different kind of contexts. So Donald Rumsfeld, did you hear about him? Some of you did? Donald Rumsfeld. Rumsfeld, it's written somewhere here. Yeah. So he was a secretary, like the person in charge of security in the U.S. and during the second Iraq War. And there was a big debate at that time about why did America actually start this war? What was the reason? And the idea was that what their excuse, or maybe real reason, we don't know, was that there's this weapons of mass destruction, and they're going to this war to get not allow Saddam Hussein to have the weapon of mass destruction. And then people asking, well, what are the evidence for that? And here's what they answered. I hope this works.
There are reports that there is no evidence of a direct link between Baghdad and some of these terrorist organizations.
There are known knowns. There are things we know. We also know there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns. The ones we don't know, we don't know.
Excuse me, but is this an unknown unknown?
I like that question. Anyway, so I brought this to explain what I mean by context. And he said, there are things that then I don't want to repeat. It's always confusing. Just look at it at home. But he categorized things to known knowns, known unknowns, and unknown unknowns. Okay? And he said, well, we have to go, there are unknown unknowns, so we always have to go to these wars because we don't know what we don't know. So then we'll figure out. Anyway, that was the logic. And the same thing happens in our brain and the environment. The context, in the sense, the context have all these kind of known and unknown unknowns. So when we come to take a glass of water, there's some known knowns. We know there's this glass and it has water, and we can look how much water there is, and we know everything, and then the brain can compute how to make an arm movement. Known knowns. Of course, also in known knowns, there's some unknowns here, but generally, all the knowledge, you can get all the knowledge by perception. Sometimes there are known unknowns, okay? And also that we need to take into account. So let's say we need to take this pot of tea. We don't know how much water is inside, but we know we don't know that. So we can adapt to that, and we can decide maybe we'll be a little bit more cautious. Maybe we'll extract a little bit more force and take into account our known unknowns. But then there are also unknown unknowns. An example? So you can think about this scenario as unknown. You walk, you don't know nothing about nails on the floor, and then there's a nail on the floor. And also that the brain needs to take into account. You can't just have a blue screen when you have a nail on the screen. You need to do something, and you can think of reflexes as a way to deal with no unknown unknowns. Okay, so there's context, and context it's a very large context dependent. There could be all kinds of contexts, and we need all the time to take them into account. Maybe that's one of the largest challenges, that our behavior depends on on the context that we're doing. So that's another example for a challenge. Here's another one. It's related to one of the previous ones, but we're not balls in vacuum, right? Or points in vacuum. Our body is very, very complex. We have multi-joint. When we need to move, we need to take all the kinematics, and the structure itself is very, very complex. We need to take all that into account. So here you see just the skeleton, how complicated it is. And here you see an example that we want to get from this point to this point, see how complicated our movements are, because we have all these joints. In this case, it's actually using them to balance, right? To fall in the right way and to be balanced in the end. It will be harder for a ball to do this kind of things, right? So we can use all our multi-joints to get to for all kinds of the advantage that we have multi-joints, but it's a very, very complicated problem. Maybe if you saw the robot in the beginning that poured the water, it had 2 joints, right? And it seemed like all the coordination between them seemed very, very complicated. Again, these are things that we do effortlessly. Okay. Next thing, and I think one of you talked about this and hinted toward this direction. There are tons of transformation the brain needs to do. There's a lot of computations that are not trivial. And when you think about it, probably large parts of the brain do things like this. We don't think we think about our brains doing trying to understand what's consciousness and true love, but probably a lot of it's going into this. It's going into this regime of just trying to transfer things from thing to thing. So what do I mean? So this is a linear way to think of a system, or maybe a robotic way to think of the system. We have some intention. We want to do something. Let's say we want to take a cup. We want to grasp a cup. So first thing, we know where the cup is in the world, right? So that's an extrinsic kinematics. We want our hand to get to the cup. That's in world coordinates. Okay, that we get from our perception, and then we need to translate that to our I called here, or Kandel and Schwartz called here, intrinsic kinematics. That means the kinematics of our hand itself, right? So there's one thing of understanding I need to bring this point to here, and then another thing that means that I need to move this joint like this and this joint like this in order to get the cup. Okay, that's a different thing. So that's what we call intrinsic kinematics, the kinematics of our arm. But again, the brain doesn't generate kinematics, it generates force. And this is what's called here kinetics, or it's also called many times dynamics. This is actually the forces that we need to extract in order to get that. And that's in the endpoint. That's the endpoint of the brain computation. Is the muscle, is the power that is the activity of the neurons that generates power in the muscles. And then we get to a response, okay? And in the next, not today, but the next lecture, I'll talk more about is the brain really organized under this dimension, but this is at least an idea. So when we think about this, this requires tons of transformation, right? Some of them you can write on you can solve on a paper, like 2-joint kinematics, or how to solve it. Others are just so complicated even to write the equations. So we have different kind of reference frames, right? We have the reference frame of the world. We have the reference frame of the joints. We have the reference frame of the muscles, right? And reference frame is something we have all the time. So we have, let's say, we think about something in the world. Now I move like this. My head and eyes are in this direction. The world didn't change, right? But what I perceived changed. So we have the direction of the head, which is one reference frame. We have the direction of the eyes. I can look here and move my eyes there, right? So that's another reference frame. And the brain needs to take all these into account in order to do even the simplest thing, right? You do a visually guided movement, you need to know where you're looking. So you need to know where your eyes. If your head is important, you need to know where your eyes are related to the head. All these are really important things. And we need to transform one to the other. So that's also very complicated in such a complicated system with all these joints. So as I said, I guess large parts of our brain are probably doing things like that, like this. These are really important and not trivial computations. Another challenge I don't think anybody mentions is delays, right? We have our neural activity is very, very slow compared to electricity, right? And there's a delay between what we see and what we actually, the time that something happened until we actually see it, for example. I want to show two examples for this and one that have some kind of functional meaning. So I want to compare two different kinds of eye movements. It comes from two different sources. One is called VOR, and I'll talk about this later when I'll talk about reflexes. That's vestibular ocular reflex. And the other one is smooth pursuit. So the examples that I give today are from R movement, which is which also I'll talk later, and also from eye movement, which is what I do in my lab. So these are examples that are close to my heart. So the first example comes from smooth pursuit, and this is a behavior that we do in order to track moving targets. So here's an example for a movie. So you have this finger, and the finger will move from side to side, and this, look what happens to his eyes. They follow smoothly the target, in this case, his finger. Okay? A bit creepy. And here is the idea of the system. What does the system do? So here you can see an eye, and let's say the eye has, you heard from Udi about the fovea, has an area which is a most dense in terms of photoreceptors, and this is the area we see most clear objects. So if you would try to follow, if you would look at a bird and the bird would move and you would not move your eyes, so initially the image will fall on the fovea, and then as the bird moves, the image will fall in a different place and you wouldn't be able to see it so precisely. On the other hand, because we move our eyes, so then the image is on the fovea, and because we move our eyes, it continues to be on the fovea all the time. So it keeps moving stimulus on the fovea. So this is the first kind of behavior. And this kind of behavior has quite long, well, it's short compared to other behaviors, but it's short, but around 100 milliseconds of latency from the time when you see something moving until you can move your eyes. Question? Okay. So that's the first example of how we move our eyes. And then there's another example. It's called the vestibular ocular reflex, which we move our eyes in order to stabilize things on the external world, but based on head movements. Okay, so when the head, let's say this is the clinical way to look at this behavior. So you have this person, and you have the doctor, let's say, holding his head, and now he's moving the head to one side, and the eyes continue to look straight, or at least it seems that they're supposed to look straight. Okay, so although the head moved, the eyes stayed in the same place, and we use this reflex all the time. Let's say we run around, and the head is all the time moving, and the body is moving, and everything. The eye are continuing to keep you're able to keep your eyes straight on your target because of this reflex. Very, very efficient reflex. Here's now again the creepy movie. So you'll see the head going up and down, and the eyes will stay in place. So you see the head is going up and down, and the eyes are continuing to watch you. So that's the idea of this reflex. And the point is, here are two behaviors. They have different latencies. So the smooth pursuit behavior is information coming from the eye and then going to the cortex. You know, there's a cortical circuit for smooth pursuit eye movement, and then it goes to the brainstem. This is maybe the fastest behavior, the fastest cortical behavior that we can measure, one of the fastest. But still, there's a 100 millisecond delay between what you see and when you start to move your eyes. And then the VOR, on the other hand, because it's a reflex at the level of the brainstem, things are much, much faster, only 13 milliseconds, approximately, between when the head starts to move and when the eye starts to move to the opposite direction. And what is nice in this is they can actually exemplify how the difference between the two. So let's do this experiment. Put your finger in the front of you. Now move your head from side to side, let's say at 1 cycle per second, and continue to look at the finger. You saw the finger very clearly. Now do the same thing, just move your finger from side to side and try to follow it. What happened? If you did the two things fast enough, the finger was blurred. And the reason is because there's this delay. The brain is not fast enough in order to compensate for these movements. It's not in the eye, right? The eye can do the movement. The eye did it in the VOR in terms of the ability of the eye to generate it. It's just the latency in the whole system. It causes this difference in the performance. Okay, so delays are important, and these are the fastest delays. If you think about, the classical example of you drive on the road, and it takes you just a half a second from the time you see the car in front of you stopped to the time you press your brakes of the car. So that means there's a very long latency of a half a second in that case, and your life could depend on that, right? So there are all these delays, and the brain again needs to take into account and maybe compensate them for some way. How could it compensate for them? Ideas. Exactly. We'll talk about that later.
But it's not exactly the same eye movement in both cases.
Why not? In what sense?
Because when I do the sports pressure, it feels much harder than moving my head and kicking.
So you told me it's not the same, and then you said it doesn't feel the same, right? So when I say the same, I mean there's same physical properties, and the same physical properties are that the muscle that moves the eye is moving more or less in the same way, right? It's moving sinusoidal movement of the eye in your head. Okay, in that sense it's the same. Now you said it doesn't feel the same, which is something totally different. And if you go to the extreme, it adds consciousness into your into your argument, which is complicated.
But maybe because one is active and the other is passive.
So what do you mean by active and passive?
When I move my eyes, I do something active, and when I move my hand, my eyes are more passive.
In what sense? One is a reflex and the other is not? That's right. So again, when you say active and passive, it depends on what you're trying to do, right? Again, in terms of physical sense, it's very, very similar. There are many, many differences, right? One is a cortical behavior. It's a behavior you need your cortex and actually to do it. The other one is solved at the level of the brainstem. And they're different, of course. They're different behaviors. They're different neural circuitry, many things different. But the properties, I'm saying that the fact that you can't follow your fingers, not because your eyes are not, the muscles are not fast enough. They can do it, because they can do it in the VOR. Okay. Do we need a break? We have another 3 minutes. Okay. So the last challenge is that, unfortunately, we need to move with muscles. And muscles are, I don't know, the engineer had some problems when he thought about that, some engineering problems that he had to solve, and he didn't use the best material probably. But muscles are complicated. They have many, many properties that at least an intuitive engineer would not try to put into the system. And I'm not going into the structure of the muscles, but I do, as I said, I do encourage you to go and at least once read it. It's interesting. It's if you haven't heard about the structure of muscles, and I think it's very interesting and important topic. But generally, muscles are complicated. I'll just say highlights. Why are they complicated? Like just differences between motors and muscles. So you can think about motors. They can move in both directions, right? You can pull and push with the same kind of motor many times. Muscles work only in one direction, so they work in pairs, right? So I move my hand like this. This muscle has contracted, and this one basically is passive at this point, is not active. So the neurons that active these muscles are now contracting and leading to this movement. If I want to do the other type of movement, then this muscle should be active and contract, and then I get the other side of movement. So this is another complication. Passive properties, the muscle has tons of, it's like a spring in a sense, in many sense. There are a lot of things that you can, unlike, I would say, a single motor where things are very metal-like and you can't stretch them, the muscle has also passive properties that the brain needs to take into account. Another thing that you think, I won't go into this also when I talk about muscles, but the amount of power that the muscle can extract depends on its length. So if the muscle is this length or this length, the amount of power that I can extract would be is different. Also depends on the velocity of the muscle. When the muscle moves in a specific direction, and it can actually extract more power. So I move my arm this direction. During the movement, I can extract more power in this muscle. When I'm going in the other direction, it's the opposite. delays, so I talked about the delays of the machines are small. Here it's 30 milliseconds. In eye movements it's a little bit less, but generally there are long delays between in the muscle itself that cause, and when you, from the time when you get an action potential goes to the muscle until the muscle actually extracts its maximal force, there's could be a long delay in some muscles. And of course, information transfer. Neurons are bad, right? They move the information very, very slow, as opposed to electricity that moves really fast. So those are the challenges, and then after the break, I'll talk about how we solve some of them, or some ideas of how we can solve problems in the brain. And as I think someone mentioned here, predictions will be important.
מה זה? בכיף. איפה אתה? אני במעבדה של יוסי בוג'ין. יוסי בוג'ין.
לא עוברים.
כן.
נשארים פה לבד.
לא יהיו אנשים שיפתחו לי בדלת.
ואתה באיזה? ב?
תואר שלי.
ואתה רוצה קורס לזה? מה תואר ראשון?
גם.
מעניין. וזה בתוכנית של מה שבדעה סופים יש?
מה?
של מי התוכנית של איזה...
כן, כאילו,
כן?
תוכנית של בהר הצופים, אבל
כן, אבל התוכנית היא מנוהלת על די הר הצופים.
כן.
שם האדמיניסטרציה שלו כאלה. טוב. Jonathan, how's everything going? Fine? Doing good?
Yeah.
Enjoying?
Yeah.
The semester is okay?
Yeah.
כמה רמות לזה. זה נושא... אפשר למצוא 100 מאמרים. השאלה בדברים האלה, מה כן, יש גם את רמת הרעש בנוירון הבודד, וגם את רמת הרעש הכללית במערכת. השאלה זה מה הקשר בין.
רעש שנמדד
פוטנציאלי פעולה. כל נוירון עושה משהו, ולא כל פעם נראה אותו.
כן, הרמה של זה.
כן, כן, כן. זה רמה של רעש יש, השאלה זה אם זאת הרמה שמסבירה את ההתנהגות. זו שאלה אחרת. שאלות, יש הרבה עבודות על זה. פריימוורק שלם רק על איך לחקור את הדבר הזה. רק רציתי לך להדגיש שיש בעיה. טוב, בוא נמשיך. קונטיניו?
זה לא היה פעם, זה היה אבן. אשכרה, זה
In the first round, we got green, but by the team that won the championship.
Okay. Let's continue. Okay. So we talked last class about the challenges, and now we'll talk about some solutions. Of course, generally the solution is, yeah, we have a big brain that does a lot of things, but we can think about concepts that are solutions. And the first one that was already mentioned is predictions. So here is an example for why we need predictions. Or examples. Sports is really, you get good examples from sports because it really shows the exact point that you want to, because the things are very discrete and clear, it makes me really understand what are the concepts and understand the points. So in baseball, the goal is to hit the ball that comes from the pitcher, right? And if what this guy is trying to do is follow the ball, he'll never get it. The brain is just too slow for that. So what they do, they actually need to look at the pitcher and try to understand where the ball is going to go and use that as a prediction for how to swing or if to swing the bat. Of course, then it becomes a game because he's trying to predict him and he's trying to fool him, and that's the idea. Another example is from tennis, right? So really naive players try to follow the ball. Expert players follow the player against them to try to understand what he's trying to do. Again, because of the problems of delays. So these are ways in which we use our predictions. We try to predict in order to compensate for delays. The predictions are also good for reducing noise or uncertainty about the world, right? Did you learn about Kalman filters in any sort? Okay, never mind. But you can think about there's always noise in the world. You can use what happened until this point and predict what will happen to cancel a lot of that noise. Intuitively, I think it's clear. And we also need predictions because our movements themselves have sensory effects, and we want to take them into account to have I would say, better behavior. And I'll show an example. I need a volunteer. Okay. So the question is here come here. So we have this waiters that holding this tray, and he has a cup on his tray. Who should pick the cup, the waiters or the customer? The waiters. Why? Because? His job. No. This is so American answer. Because you get paid for that. But he sees that I'm coming, picking up. He can balance it anyway. Okay, so here's exactly. Right. So he knows exactly what he's doing. So here's the example. Hold this with one hand. Are you strong? Okay. Hold it with one hand. Now look at your hand. I'll pick it up really fast. Look what happens to the hand. Went up. Now you do the same thing with your other hand. It stayed in. Okay. Thank you. So that's why we have this book, really important book. Has a goal. Yeah. So read the book. A lot of the material here, a lot of what you learn comes from there. Read the Principle of Neuroscience. Each time I learn something new from it. And you can also use it for it. So the idea is that when we know what we're doing, when we have good prediction from our own motor system and our own brain, we can compensate for that, and we don't, because she, remind me your name? Chen knew that she's going to pick up she's going to pick up the book, so she could compensate that, and she already, while she was picking, she already extract less power. On the other hand, when I did it, she knew that I'm going to do it, but she didn't know the details of when exactly and how, and then the power was, the hand went up because there was too much power. It took her some time to compensate for the mistake. Okay, so that's prediction, and generally, this is so prediction, I said we all the time want to predict the sensory consequences of our movement. And the idea here, and this is another concept, there's a efference copy. So our motor system sends commands to do something, and also sends a command to the own system in order to use that to predict what will happen in the future. And here is maybe the first example. That was the first one that came with this concept was Helmholtz. Did you see him before? Did you recognize him? He was the guy with the big eyes, right? It's the same person. And the idea now here is that when we move our eyes in the world, we all the time feel the world is stable. We predict the movement of the eye, and because of that, each time the eye moves, we don't feel that the world is moving. On the other hand, if now, and do this carefully, don't do it with a pencil, if you just push your eye a little bit, let's say close one eye, or if you want like this, and then push your eye, really gently. I don't have insurance for this. So do it very gently, and you'll see that the world is moving, right? Again, we're doing, in a sense, the same kind of behavior, or relatively the same kind of behavior. In both cases, we're moving the eye. One time we're doing it, and then the world is stable. But when we're doing it in a non-regular way, and the way that the brain didn't learn to predict, the whole world is moving because we moved our eyes, right? So the world is moving because the image on the retina is changing, right? So the brain interprets that as the world moving when it doesn't move itself inside. So that's one example, and here's another example. Did you try ever to tickle yourself? That's impossible, and the reason because you predict your movement, right? You're predicting your movement, and the brain takes it into account, and it doesn't, and it knows that something will happen, and doesn't feel as tickling. So this is an experiment where they did a tickling machine. So they had like someone move his hand, and then there was a delay between the time that he moved his hand and the time that a machine tickled his hand, I think, or his other hand. And then they asked him how ticklish was the behavior, or how ticklish did the sensation feel. And when there was zero lag, when you moved your hand exactly, the machine at the same time tickled you, you didn't feel very ticklish. But when there was a large delay of already 300 milliseconds, it felt much more ticklish. Okay, so the idea is that the timing is really important. When, right, the timing of when you made the movement until when you felt it is really important. And some timing, the brain gets used to specific time windows, and that's what it used in order to compensate for the sensory information. And when you think about it, all your movements, whatever you do, all the time get the sensory information. When you do it, you can compensate for that and predict how it will change the world, and predict the next state of the world, so we won't be surprised in order to control all the world. Okay. Another way, so we talked about a prediction. Another thing that we do, the world is changing, and we learn, there's a lot of motor learning. We learn to do new things. We learn all the time. This is a classical example of learning how to ride a bicycle. So who's learning here? You think the daughter's learning, but actually the father is also learning really hard how to teach the daughter. Not trivial, but generally there's the idea of motor learning, of that we initially the girl did not know how to drive the bicycle at all, and then through practice and error and falling a little bit, it's really hard for both the teacher and the daughter. They learn how to ride a bicycle. And motor learning, and the question is what's happening in the brain, what is changing. Here's an example, a paradigm that is used often in labs. I think I'll talk about it also, and when I'll talk about motor systems. So this is just a very famous example of motor learning in the lab. So generally, when we have these concepts, we want to put them we want to bring them to the lab in order to really understand the details of what's happening. So in this task, we have this subject holding a bar, and he needs to move the bar to one of 8 directions. Okay, very simple task. And you can see here, initially is movement, very straight movement. So this is another property of the motor system. It tries to do more or less straight movements. And then what the experimenter introduced is a perturbation. And this is a perturbation where the power is orthogonal to the direction of movement. So let's say I'm moving in this direction. The power will be orthogonal. And the faster you move, the larger the power is. Okay? It seems not intuitive power. And although, if you think about it, in the world there are situations where we feel this kind of power. It's called Coriolis power. Anybody hear about it? So imagine you're turning around and you're moving your hand while you're turning around. The further away you're moving your hand, the more power you feel. So that's kind of simulating this situation. So, but still, it's not something that you used to. It's something you need to adapt. Your motor system needs to adapt to it. So, initially, here you can see the pattern of behavior. Initially, after the first exposure, you see the movement are not as nice, not as straight as the one before. You see this? The power just pushes the hand a little bit, and then he has this correction. Okay? So that's in the first exposure, and then there's a period of adaptation where you continue to move your hand like that, and you continue to experience this force, and then again the behavior becomes straight, like in the null field, like in the regular condition, meaning that the subject here learned the force field and was able to compensate for the power of the force field. And what is also interesting to see that he really learned something new. It's not just using the sensory input about the specific position, specific point. What we often see is the after effect. So now that you turn off the force field, you see that the arm is moving in the other direction. Okay, so that's That's one example of motor learning. And this is an example that really, it feels like a motor example. It's movement in the world. Often people can't even say if they don't even understand they can't even say what they learned. They just say, we learned there was some kind of force and we learned to move straight. But they can't really say, I moved this muscle like this and this like that. It's very, I would call it procedural learning. And there are all kinds of different types of motor learning. You can think about almost anything that you learn in life as a motor. There's a motor component, right? Even when you study, you sit here in front of me and you write on your notebook, there is a motor component to what you're doing. But there are differences between the two, right? There's a difference between learning how to ride a bicycle and sitting here and learning. And maybe the way that was shown, one of the first ways to show that there is really different things came from the case of HM. All hear about HM? Anybody not hear about HM? Okay, so HM was a subject that had epileptic seizures in the temporal lobe, and then this is like I think 50 years ago, and then at that time the way to treat was to take out the area, to dissect it, and they took out his hippocampus and areas around the hippocampus in both of the temporal lobes. And what it found out that after that, what happened, the side effect was that he couldn't remember anything anymore. Couldn't remember people. You would come to him every time you would come to him, and you would think it's a new person. Okay, and then after that, so that happened, and then there was a researcher. Her name was Brenda Milner. She's still alive, I think, like 100-year old. I encourage you all to go to look at his very nice YouTube movies of her talking. She's very impressive. And so she came, let's see. So he can't remember who the experimented. Let's see if he really can't learn anything. And what they did, and the task that she came up with was with this kind of task. So what he's supposed to do is track the star, okay? But he's not looking at his hand. He's looking at a mirror. So he needs to do like a mirror image of what he's used to seeing. And initially, people are not good in this task initially, and maybe I can. Do we have a volunteer here? Another volunteer? Leo. Let's try to do this. So, move your hand, try to follow the star. Look here. Yeah. Let's see if this will work. Look in the star, and everybody will see how you track the. Ah. There's another component. Okay. This is the harder test. Okay. So you can do it very simple, right? This is just looking. Now, let's try to do it this way. Let's see if you won't be able to see it. I can't show it. Maybe. Okay, let's return to this later. I want you to do it when you're looking at the screen while. No, never mind. I'll do it again. We'll do it. I'll put the. If we'll have time, I'll put the mouse, and then we'll work easier. I just turn on. So sorry. I had to prepare for that. But the idea is that you can do it at home. Take a mouse, try to move, follow the star, and then turn the mouse around. Okay? Just turn the mouse around and try to move it. It will be really hard. I just need to set the mouse here, and I didn't. Okay? So that's like, look, you're making your movement opposite to what you're used to, and it becomes really hard. So so people can learn this, and then Brenda Milner came to HM, and I told them, try to follow it in the first day, and it was quite bad. And then the next day she came again and told him, I tried to follow the star, and he said, well, I should, this is like, she asked him, did you see the star ever? He said, no, I never saw that. This is the first time I'm doing it. But what she found out that he was improving. Okay, so this is like the first day, he's improving, and then the second day is not starting from this point. He's already improved. Although he doesn't know what the star is, this is the first time he thinks he is in this kind of task. Although he's not aware of this, he already improved with this learning. So the idea is that after that, the idea is that we can split our types of motor learning or type of learning to procedural learning and declarative learning. Learning that we can say what we're doing, and learning that is more related to what we're doing. And after that, there's a whole field of splitting memory to different types of giving a different name. But the reason I bring it because it captures our intuition that there's something different than learning how to ride a bicycle and learning in a class. And that's a nice example to show that.
Which was his?
So he couldn't, the declarative learning, he couldn't say what he learned. He couldn't remember the experiment. He couldn't remember what the task, you would ask him. He couldn't declare what he learned. And generally, like we ask yourself, what are we learning when we learn how to ride a bicycle? It's hard to say, right? You just do it. So that's procedural learning versus things that you can, like in the class, you probably it's more declarative. You can tell me what you learned. I hope. Okay. So that's about a general introduction. How much time do we have? Not much. Okay, so now I want to go a little bit into more details, more going into the bits. Maybe I'll continue this in the next class. We'll see how much we get. Okay, so that was a general introduction. Now we want to talk about what actually happens in the muscles and in the brain. And the first thing I won't talk about the really mechanism, how the muscle is contracting, but I will talk how the brain controls it. What determines the power, the strength of a muscle contraction. Here are five different things. So what will cause more power in a muscle? So the size of a motor unit, and I'll explain what it means. There'll be more, the larger, the stronger power we make, we need to recruit more and more muscle fibers. We can control the muscles by changing the firing rate of the neurons. Different types of muscles have different power. And I won't talk about the fifth, but the muscle length, and I've mentioned it, the muscle length will determine the amount of power that a muscle can have. So I'll go over each of these one by one and give examples. But now, so just to orient you again, we finished the introduction of the introduction. Now we're going into the details of how the brain controls muscles. So the concept of motor unit, did you ever hear about this? Okay, so we have each neuron in the, let's say, the spinal cord, innervates several muscle fibers, and each muscle fiber gets input from one neuron. Okay, in adults, in childhood, during development it's different, but as adults, each muscle fiber here, each cell gets input from one neuron, and the motor unit is the neuron and all the muscle fibers that it innervates. So in this example, we have two motor units, one blue. See this neuron? that's connected to these 2 fibers, and we have another green one that's connected to these 3. And this is maybe the first time we go back to Sherrington. So Sherrington is the one that came with this concept, a very, very fundamental concept of how the brain controls the power. And the important thing is that different muscles have different relation between the number of neurons and the number of fibers. So for example, in the leg muscle, and these are approximations, and Kandeln-Schwarz, you can get the more accurate number for different muscles. For one neuron will be connected to around 1,000 muscle fibers. So it means that activity of one neuron will cause activity in many, many, many muscles at the same time. So a lot of power. In when we need finer movements, like in the finger muscle, the ratio is much smaller, and in the eye muscle, it's the smallest in the brain. So because we need really, really accurate movements of the eyes, because any tiny movement in the world will change what you see, the ratio is much smaller, 1 to 5. There are even neurons that are connected to a single fiber, so one neuron that is connected to a single motor cell, a single muscle cell. Sorry. Okay, so the amount of power will be determined by the size of the motor unit, and this is important because for fine movements, for really, really fine movements, we need very, really fine control with that allows that, and when we have a small ratio, we can do that kind of fine control. So that's the first thing. The second thing is the activity of the neurons itself will decide how much power is extracted. And there are 2 points here. One is that when we do a movement, more and more neurons are activated when we do a larger movement, and each neuron will fire more and more spikes. And I want to show this from the eye movement system. So what you'll see here is the activity of one neuron, a motor neuron. This is a neuron here, this green one, let's say, that activates this muscle. Okay. So when this neuron is activated, it's a motor neuron. This muscle will contract. So what you'll see here is a monkey. The X represents where the monkey is looking. The square represents the target, where it's looking at. Okay? And at the same time, you'll also be able to hear and see the activity of one motor neuron. And you'll see that the target will jump in one direction and listen to what you hear in the neuron. I'll show this twice, so it'll be clear. Okay, so here's the movement. So it's fixating on the point. So each time the eye is moving to the right, you see very strong activity. Okay, was that clear? Do I need to explain again? Okay, I'll explain again anyway. So what you can see, so here you can see the activity of the neuron, the spikes. Each line here represents a spike, and you can see here some average firing rate, some average activity. And when the eye moved to the left, and this is these areas, the neuron shut down. You can see places where it was completely shut down, like here. See, no spikes at all. On the other hand, when the eye moved to the right, you see how the activity was enhanced, was very, very strong. And there are 2 points, as I said. First is that at some point the neuron did not fire, right? That means that at that point, the neuron has zero influence on the muscle, right? On the other hand, the more we move to the right, the more and more activity there is in the neuron. I'll show it again because I really like this movie.
The recording is from the spinal cord?
No, the recording, these are, okay, so I'll talk about that later, but this is from the brainstem. So the spinal cord controls the trunk and the arms and legs. The brainstem is the equivalent for controlling the face and the eye muscles. So this is recording from the brainstem. At this point, this is the brainstem. From it's called the abducens nucleus. This is where the pool of motor neurons that innervate this muscle, which is called lateral vectors. The names are not really important. These are motor neurons that move the eyes to the right. That's what is important. Let's again, okay? So you see, there is some, when he was looking straight, there was some activity, but then it increases when he moves to the right. You can also see that during the movement itself, there's some burst of activity. You see that? You hear it? You can also see it here. And that's another point, that during the movement itself, the brain needs more power to extract more power in order to move the eye. And in this case, you need more activity when the eye is moving more to the right, because the eye is like a spring, and if you would not have more contracting of the muscle, then it would just drift back. Okay? That's why we need this kind of activity. And the two concepts to learn from this are quite simple. The first one is that there's a concept that's called recruiters of motor neurons. When each motor neuron has a different threshold in which it will start to activate, and that's what's exemplified here. So here we have two neurons, one blue, one red. And let's say this is similar to the experiment that we did here. The x-axis is the eye position. This is to the right. This is to the left. So when the eye is on the left, this red neuron is not activated at all, so it's not recruited. On the other hand, already at, let's say, 40 degrees, the blue cell already is recruited. It passes the threshold for activation, and it starts to fire spikes and lead to more power in the muscle. So that's the recruited motor neurons, and different neurons have different recruited thresholds. It's true also for arm movement, not only for eye movement. Also when I try to make some kind of, I'm trying to hold something. If I'm trying to hold it lightly, then very few motor neurons are activated. When I extract more and more force, more and more cells are recruited. So that's the recruited motor neurons, true for eye, true for many muscles. Also arm movements. A general principle, important principle. That's the first thing. And the second thing that you notice that the firing rate was stronger, right? The more, in this case, it was linear. The more the eye was to the right, the higher the firing rate was. More spikes per second the cell had. In this case, it's linear, which is interesting. It doesn't have to be linear. Linear in the sense that as the eye moved more and more to the right, the firing rate increased linearly. That's true for eye movements, not for general. But generally, it is true that when you move more and more when you need more and more power, cells fire more and more. So this is the two cells. This is all the population you see. Different cells have different slopes. Okay, so we see that brain can control by adding more and more, recruiting more and more neurons, and by increasing the frequency. The frequency also has an interesting interaction with the muscle itself. So this is an experiment where you have a frog leg. You put it on like this. You connect it on one side to here and the other side to here, and you have something that measures the power, usually here. Okay. So and then you give a pulse to the nerve here that activates the muscle. So that's the experimental setup. Quite simple. So here you can, and then when you give a single pulse, you get what is called a twitch. Okay, so you get some kind of amount of attention that you can measure. This is the time from the stimulus. There's some latent period, which is a delay that's caused from all kinds of stuff. Not important now. If you're interested, read it in a book. Because it's not instantaneous. There's a synapse there, and there's all kinds of things that need to happen. But then after that, the power starts to increase. Okay, and then relax, and this is called a twitch, the response to a single pulse. And different muscles have different twitches. Muscles that you need to activate really fast, like the eye muscle, has a very fast twitch. A saccade, a movement from one side to the other side, the whole movement is around 40 milliseconds. So you need the muscle to be really, really fast. On the other hand, if you look at leg muscles, they're much, much slower. This one takes about 40 milliseconds until it gets to the peak. When you don't need behavior to be very, very, very accurate or very, very fast. So that's a twitch. That's a response to a single cell. And the question is, how does this accumulate, right? I think you learned the neurons, right? There's an EPSP, and EPSP could sum to action potential in some cases. In this case, we're not talking about action potential. This is all after the action potential. This is already the force itself on the muscle. But even at the level of force, there's an interesting way in which it happens. And this is what you see here. So this is an experiment where initially you just give 5 pulses at 5 hertz, okay? And you see there's a twitch, another twitch, another twitch, and another twitch. And then you increase the frequency, and now the twitches start to sum. And you can increase it even more. They can sum until in the end, when you increase it enough, it gets to a maximal force, and it becomes very, very smooth. That's what you see here. So this kind of behavior is called tetanic contraction. When you get to the maximal contraction, and I'm not going into the details of what's happening here, But each pulse causes some cascade of events that cause the calcium to be released in the muscle, and that's what causes the contraction. At one point, you get to the maximum amount of calcium. You can't activate the cell more than some amount, and that's the point where you get to a tetanic contraction. So again, there's an interesting relation between the firing rate and the activity of a single cell and the actual a pattern of behavior that you get. What's going on? Could you close the door? Thank you. Okay. Water leaking. Is anybody willing to let Neely know or somebody? Are they working on it? Okay. So let's continue. So we said there's recruitment of motor neurons. The frequency itself is not that a single spike causes a very stereotypic behavior. There's some process of accumulating spikes that leads to this kind of a behavior, from a twitch to a tetanic contraction. Another important thing is muscle type. Not all muscles are equal. They have different properties. There are some muscles that cause a lot of force and also work very fast. So we call their fast twitch. They have this very fast twitch. You see it? And there are other type of muscle that cause a slow twitch. So these are categorization, like in many things in biology. There are all kinds of categorization. In the end, it's understood these are distributions of behaviors, but this is just the categorization. This is what you need to know for now. So we have some muscles that are very fast and some that are slow. So they were divided to fast twitch and slow twitch. So time, this is x-axis here is time, and y-axis here is a tension or the power. And you can see this one is fast, this one is slow. Another thing that you can notice is the range here. This one has 100 something Newton, and this one is only 5. I think this is Neely. So there's a big difference in the range of the power. So this is much stronger. So that's one thing. And the muscles can also be divided into if you look at the way the way it accumulates. So we take the fast one, and we can see that they make a lot. But if you just now have a very, very strong, a lot of stimulation, you get a very, very large power, as you can see here. Whereas you have others that it's lower, and they have some slow ones. Okay. And then there's also difference in how much their fatigability, how much they become fatigued. So the fast one, the one that extracts a lot of power, will get fatigued really fast. So you see here, the experiment here is that you give the same kind of stimulation for a really, really long time, and then initially the power is very large, and then it declines. In this one, here there's also some decline, but not much, and this one is just constant. So why do we need different kind of muscles for what kind of behaviors? What muscles don't we want them to be fatigued? Never, ever. Heart, well, we're talking here about a skeletal muscle. So heart is a different story, it's a different mechanism. Like? Balance, right. So I'm standing here, I don't want to fall in the middle. It would be nice to me. I won't enjoy it. Right? So there's a lot of things like balance. We want to be able to keep them for a really, really long time. And balance is not just me standing. Also, when you're sitting, you're not collapsing, at least most of you. So these are things that we want to work for a really, really long time. On the other hand, we have muscles that we want to work really, really fast and for short periods. So, for example, if you look at people running 100 meters in the Olympics, there are different kinds of muscles. It's not the balance muscles that are activated. It's these fast twitch muscles that are activated. They can have a lot of power, but for really short periods. And there are tons of histology differences. So you can look at the muscles themselves, and you can see differences in them. I don't want to go into this in detail for lack of time. But again, go to the book, to Candela Schwartz. There's a good chapter about that. It's interesting. Okay, so that was the muscles, the properties of the muscles. I want to talk about now the simplest behavior, reflexes. I give examples for 2 reflexes. The stretch reflex. Did anybody here not learn about the stretch reflex here? Did you all learn about the stretch reflex? No. Let's ask it again. Who did not hear ever about the stretch reflex? Okay, I'll explain it. Okay, so here's the stretch reflex. It's maybe one of the simplest behaviors that we have. Where's the Leo? Now I can. Now we can use you. Let's see if I have a. Let's see if this will work. Don't sue me after this. Sit here, sit on the table, yeah, and hold it. Put just. Okay, the idea is I'll try to. Saw the leg moving? Yeah. Okay. Thank you. So that's the stretch reflex. Let's see what happened here. So it's a reflex that it happens at the level of the spinal cord, and we have usually it's some kind of hammer, a small hammer that you hit the tendon here. Okay. As a result, the muscle length, this muscle becomes longer. Okay. That's what you see here. In each muscle, there are elements that's called muscle spindles that what they do is measure the length of the muscle. And once I hit here, the muscle became longer. This is the muscle spindle. In the muscle spindle, there are these neurons. Let's see, where are they? These neurons that report that the muscle became longer. So there are action potential in these cells. And then this is what you see here. So these are the sensory neurons that tell you the length of the muscle. This is again part of, we have a sense of proprioceptive sense. Did you hear about that? Of where our body is in the world. Again, Sherrington is the one that coined the term. So this neuron starts to fire because the muscle is longer, goes into the spinal cord. The spinal cord has a dorsal horn where the sensory input goes in, and has a ventral horn where the muscle, where the motor neurons are. So it goes into the dorsal horn, connects directly to this cell, okay, an excitatory connection, and then this is a motor neuron that activates the same muscle, okay. Now, as a result, so what happened? We hit here, we got this reflex, activity went here and activate this motor neuron. What will happen to this muscle? Will it shorten, right? It will contract. And what will happen to the leg because this muscle contracts? Go up. Okay? And at the same time, so in our muscle system, everything happens in pairs, as we said. So when we activate this cell, when we activate this muscle, we want to deactivate this muscle or not activate it, right? So we have here also interneuron, this one, which is an inhibitory interneuron. Okay? So when this cell fires, the sensory cell increases its firing rate. This interneuron also increased its firing rate, and as a result, this motor neuron decreased its firing rate. Okay? And then there's no spiking here, and as a result, this muscle is not activated. Okay? So and then inhibition is not on the muscle itself. In our nerve system, we don't have direct inhibition on muscles, and crabs, I think they do have it, but not in these muscles. So then you have this cell is not activated, and as a result, this muscle is activated, this is not activated, and the leg goes up. So that's a simple reflex. Yes?
The first, on the upper muscle, the first nerve, it goes from the spindle, and the one that's returning is going to the
to the muscle.
muscle.
Yeah,
right?
yeah. I don't want to go into complications. There also the spindle itself has some motor input. So you want all the time the brain to be able to calculate the length of the muscle. So when the muscle is shortened, also the spindle becomes shortened and becomes less sensitive. So there are special motor endings in the spindle that allow you also to contract the spindle at the same time you contract the muscle, and to allow it to keep more sensitive. If you didn't get that, it's okay. I won't ask about it. It's like I need 10 minutes to really explain it. Okay, so that's the reflex. What is it good for? For drinking beer. Here's the example. It stabilizes joints, right? So this is just the reflex. Now you're holding a cup. Now I add something to the cup, and it should be automatic. The reflex in real life it's more complicated, but the reflex would work in this direction. Now this muscle became longer, right? We have this reflex that goes back to the muscle, and the muscle will go back to its previous location. So it's a way to stabilize your muscles. I think somebody mentioned in the beginning. So this is a simple reflex that's happening in the brainstem, And when we're controlling each of our movements, we need to take this reflex into account. Okay, so our brain, it's not acting on balls and world, right? It's acting on something that has an internal circuitry, an internal mechanism inside itself. So the way we control behavior is not by just sending a command and do it, but the command itself needs to take into account all this reflex. Maybe if you now, so we don't, maybe now I'm holding a cup and I want actually to move my hand, this reflex is basically blocking any movement of the hand, so I need to control the reflex itself for doing any movement. So that's a general, but again, that's a general principle that the brain or our motor system is a hierarchical system. It has computation elements at its core, basic computation at its core that the brain needs to take into account in order to actually do movement. So that's one example, and I promised another example from the vestibulo-ocular reflex. So this is again a reflex. We said it's a very fast one of 13 milliseconds, and this is how it works. So first, this is just a movie showing the activity of one cell during VOR. So what you see here is the position of the eye, and this is the position of the chair or the head of the eye. The head, and what we're doing here is rotating the monkey on a chair like this, from side to side, and at the same time it needs to continue and look straight. Okay, so we're activating the VOR. So we're rotating it here, and you'll see the chair or the head moving from side to side, and at the same time you see the eyes more or less in the center because of this reflex, or using the VOR reflex. And at the same time you can hear the activity of one motor neuron. So here's another movie that I like. So in this case, it's a motor neuron that's to the left, from the other side. So each time, am I right? No, this is the right side. Okay. Sorry. So that's the reflex. So what you saw here, the activity of the neuron, while the eye was staying in the space in the direct gaze, and when the chair or the head was moving in this direction, the eye had to move on the other direction, right? So that was the VOR. And what are the neural mechanisms for that? So let's see how much time we have. 4 minutes. I'll get a little bit. So the idea, we'll talk, the sensor for the vestibular information is in the inner ear. It's called the vestibular sensor. Here you can see it. This is in the inner ear. I won't go into the details of what's happening here, but it's basically it's fluid that's moving in your ear that leads to activity in sensory neurons. So that's the vestibular organ. And from there's a direct pathway from the vestibular organ to the eye movement, and the way it works, it's very similar to the stretch reflex in terms of the concepts. We have here a movement to the left in this case, okay? We have the sensor here that can measure this movement. Okay, so activity of the cell here increase their firing rate. This is the sensory neuron, goes into the brainstem. So the analog of as I said, the analog of the brainstem in these kind of movement is the analog of the spinal cord in these kind of movement is the brainstem. It goes into a nucleus called the vestibular nucleus. Here it's synapses on a neuron that is connected, goes to the other side. This neuron is connected to the abducens neuron. These are this is the pool of the motor neuron, and this activates this muscle. Okay, so it's a simple pathway. Here there are three neurons, 1, 2, 3, that activated the stretch reflex. We had 2 neurons, right? So in this pathway we're activating this neuron. The names are not important at all. If you don't know what vestibular, forget about it. In different course, maybe you learn about it. Just the idea that we have sensory input going into the brainstem, activate in an activation pathway, driving a muscle. But when you think about it, we need to coordinate different muscles as we did in the stretch reflex, right? We need first, when we're activating this muscle, we need to deactivate this muscle or to not activate this muscle, right? Because we want the eye to move this direction. At the same time, we also want to activate this muscle, right? Because it's the other eye. We want it to move with this eye. And we want this muscle to not be activated. So there are also pathways in the brainstem that do that. One interesting pathway is from this motor neuron pool, there are some neurons that go to the other side, go to this nucleus, and then activate this muscle. Could he wait 2 minutes? Oh, no. Okay. Okay, anyway, so that one coordination level is between two eyes, and that's done by this pathway. At the same time, we want to inhibit the other pathways, and there's also pathways for inhibition, right? Like we had before. We had a pathway for exciting cells, and there's also a pathway, a different pathway that inhibits these cells that are then exciting the motor neurons, okay? A little bit more complicated, but same idea, that we have an excitatory activity activating an inhibitory neuron that inhibits the motor neurons that are for the antagonist muscle. So that's the general idea of how these are the simple behaviors that we need. These are the simple reflexes that we want to control. So when you think about it, I can keep my hand and move my head, right? So that's when I'm using the reflex. But I can also do this kind of behavior, right? I'm moving my head and my hand together, and then I need to compensate for that. I need to take into account the fact that there's a reflex when I do that simple movement, right? Because now I'm actually canceling the reflex, right? I'm moving my hand and my eyes together. So that's another example. So how does the brain do it, and what are the mechanisms for doing it? But the way this is my belief, and this is maybe I'm biased here, the way I think we need to think about these systems is to understand what's happening at the low level, and only then we can understand what's happening above. Without that, then you can come with all kinds of hypotheses, but when we understand the level of the reflex, we can maybe understand how to control the reflex or how to control voluntary movement. So when I did this is a voluntary movement, right? I decided to follow my hand. And that's related to what you said in the beginning about passive and active. These things are related. So we can think about our will as an active process, but it needs to take into account all these passive properties. And I think we're done. בוא ננסה את ה...
זה השני, לא האחרון, הרחוב.
רק איזה אמריקאי
כן. תלוי מרצה, כן. אני אגיד להם שהם יכולים לעשות גם וגם. אני אמליץ להם לעשות אמריקאי, אבל אם הם ירצו לא לעשות אמריקאי, אז זו זכותם. אני אגיד לכם, אני מראש, כן. אבל תתכוננו גם וגם. אני לא יודע אם הצורת לימודי אחרת באמת.
אחת להבין את האמריקאית, אני שלי לפחות, אחת להבין את הקונספט, והשני צריכים להבין את זה למוד בעל פה. שם לא היה שם הייתי צריכה ומה ישתתף, בשבילי זה אבל אם זה אמריקאי אני רואה לפי הקונספט האמריקאי
טוב, לא יודע, אני לא רוצה.
אני
זה לא יקרה.
זה לא בסדר, אבל זה לא טוב. זה שלושה קורסים. You can. Oh, what's your last name, by the way? What?
W-E-I.
W-I.
W-E-I.
E-I?
Yeah, W-E-I, wait.
W-E-I.
Yeah.
Okay. Short last name. All right, so we'll talk on Tuesday?
Yeah, Tuesday.
Right, that's what I have to look myself for. Remember, maybe it's Monday, one second.
Monday afternoon, yeah.
Wait.
Monday afternoon.
So tomorrow,
Yeah, Monday afternoon.
tomorrow, yep, at 2 o'clock.
2 o'clock, okay. Talk to you tomorrow.
Right, buddy.
אחרי זה, עוד פעם הלכתי אליו, ישבנו כמו וזה, אומר לי, תשמע, אני צריך לנסוע, חצוף! סבתא שלי נפטרה, אני הולך. תגיד, רונן, איפה הפירים? שם זה פירים, נכון? אחד 5 מטר, אחד 15. זה 15, זה פירים. לא, זה הראשון. איפה השני? יש שני, שהיינו בפנים. אחד עולים איפה מעלית? לא. השני זה שם. איפה מעלית? מאחורי המעלית. איזה מעלית יש? איזה מעלית זה הצד? איזה מעלית זה בצד הזה? מאחורה נמצא הפיר הראשון. נכון? לא, זה השני. זה
Great, thank you.